Hello.
Hello.
Hello, Mr. Ryan, right? Okay. So we give you an array of numbers like 1, 5, 2, 3. Okay, listen. So we want to find out if at most, by removing at most one element, can we have the remaining numbers strictly increasing? So you can remove at most, yeah? You can remove at most one element. And the remaining needs to be strictly increasing. Yeah?
What if it's already increasing?
That's a very good question. Yes, if it's already increasing, then we return true because look, at most. What's at most? It means that you don't need to remove it. You can remove 0 element. So, should I return yes or no for this?
Yes.
Yes. Why is that?
Because you can remove 5.
Yeah, I can remove 5.
And then it will be
1, 2, 3. Strictly increasing. Okay.
1, 2,
What's
3.
strictly increasing? If look 1,
It
2,
means
2.
strict.
Is this strictly increasing?
No.
2 and 2. This is not strictly increasing. Well done. Okay. How about this? 1. Let's say 1, 5, 2, 3, 1. Okay. So
No.
can we have the strictly increasing array by removing at most one element?
No.
Yeah. There's no chance, yeah? Because look, if you remove 5, 1, 2, 3, 1 is not strictly increasing. If you remove 1, 1, 5, 3, 3 is not strictly increasing. Okay, so what's your approach to do this? What's your approach? Yeah? Any idea?
Well, grid.
Great.
Brute forcing.
Brute forcing, yeah. So what's brute forcing? We can, I mean, we can just try. There are n numbers. We can. How many choices can we try? How many choices? N, obviously. Yeah. If not n numbers, we can try and we can try and removing the number, right? So we can have n choices to remove each number to see. We remove that number and then we try to see if the remaining is strictly increasing. Yeah. Yeah. Right.
Yeah.
Okay. So first of all, how do we check if this is array? How do we check this is strictly increasing? Come on. Define. Let's say it's sorted. Yeah. It's increasing. Okay?
ARR.
It's increasing. Okay. It's increasing. It's increasing. ARR. Okay. So how can we check this? The numbers are strictly increasing. Alright. We given an array. Yeah. How do we check if this is strictly increasing? How do we check? If we want to know a number is strictly increasing,
So you just travel one by one.
and then we compare what? Compare,
The first with the next one.
and then secondary, yeah? Yeah. So we just compare. Look, 1 smaller than 2, yes. 2 smaller than 4, yes. 4 smaller than 5, yes. 5 smaller than 3, no. Return false, easy. Okay. Yeah. So look, n equals the length array, and then we want to return what? Return. We just do this. Okay. For I in range n minus 1. Yeah. Why is n minus 1? Because I need to check the number and the number next to it. So look, if ARRI is bigger or equal than ARR I plus 1, right? If this number is bigger or equal than the next one, and we return false, right? Yeah? Otherwise, we return true, right? Look here. Look. Yeah, makes sense? So we're traveling from the beginning, the index, and then if we find out this number is bigger or equal than the next number, it means that we have what? We have a reverse. We have a non-increasing. Yeah? We have a non-increasing order, so we return false. If there are n numbers, what's the time complexity? What's the time complexity? Come on.
N.
Oh, and very obvious. Okay. Okay, so we can simplify this. Yeah, this is okay. This is very traditional, very classic, textbook. But in Python, you can do it simple. You can say return. I want all. Okay, all. This is the keyword. All means everything inside needs to be satisfied. So all what? All ARR I needs to be smaller than ARR I plus 1. Yeah. for I in range n minus 1. Okay, so this is the opposite. So look, which one you think is easier to understand? The both the same thing. Look,
The right one
right one. Okay.
is longer.
This is the check. So we are checking the violation here, right? Yeah. If we find something that violates the increasing, then we return false. Otherwise, if all check pass, we return true. But here it's more like human language. Return all. All means everything in there needs to be true, right? Or so array I is smaller than array I plus 1 for I in range, right? So everything in this condition is true. Okay. So similarly, we have another similar keyword called any. So if we say return any, it means that if one of them, at least one, occurs true, then return true. Okay, make sense? Or means everything needs to be true, and means, if we find one, that's okay. We return true. Okay, yeah. On. So now look, we have this on, and we go through this array to remove it. Yeah? So we can say for I in range n. Now look this one, yeah. The array is 1, 1, 2, 3, 4, and the index is here. Index. So how can we remove this number? If we remove the index at I, what's the remaining? Okay, then I put a 0 at the beginning. If I want to remove this 1, okay, this is ARR, okay, and I index is 1. I index 1. 1. Okay, so what's the array after removing 1? It'll be what? It'll be current array will be array up to I, not including this one, right? Up to I. This one is here before, right? And then I want to concatenate the numbers right after I. So plus ARR. What?
Plus ARR.
This is I plus 1, right?
I plus 2, I plus 3.
I plus 1. Okay, so look, Eric. Look, we have n choice, yeah? So if we want to remove the index number at index I, right? So the remaining numbers is current, which is ARR up to I plus ARR I plus 1. Okay, so what's this? Come on. What's this?
ARR I.
What's this COR mean?
Current.
Yeah, what it is? What's this? Look.
It's the current.
So do you understand this bit? I for I in range n. ARR up to I means this bit. ARR I plus 1 means this bit. So if I put these two together, what does it become? What do we have?
Sorted list.
So no.
Strictly increasing width.
So we want to check we want to prove false, as you said, yeah?
Yeah.
We want to prove false. So by prove falsing, it means that we can try removing the element, yeah? We can try removing the first element to see the remaining is sorted. We can remove the second one, remove the third one. So we remove the element at index I. So what's this COR means? COR was I want to remove this index element at index I, and then this is AR up to I, this is AR I plus 1. So if I put these two together, what does it become? What's this COR mean?
It's the
The
array I plus array I plus 1.
yeah, so it's the same thing as removing
No.
removing array I, yeah? Yeah, that's what I said. And then we just check if increasing is increasing, increasing, we have to define this function COR, then we return true, right? Okay, otherwise return false. What's the time complexity? Come on, if all O(n) square. We're done. Look, this is O(n). We have n choice. But for each one, we need to call this. This takes another O(n) time. N times n O(n) square. Okay. Easy peasy. Okay.
That'll be it for today. Bye.
No. We have a faster approach for that. Look. 1, 5, 2, 3. Okay, let's go back to this example.
Yeah.
What's the longest increasing subsequence. Remember we talked about this.
1, 5.
Longest increasing subsequence. Longest one.
1, 2, 3.
Okay, so what's the length of the longest?
3.
3. Okay. And how many numbers are there? 4. Right?
4.
Okay, remember this. Okay. Okay, I'm going to give you another one. 2, 10, 3, 4, 6. What's the longest subsequence?
2, 4, 6.
What's the length?
4.
4. What's the total length?
5.
Okay, so what's the
You do what you just did and then check if
Just minus
if it
1.
if it
Where down,
difference is 1.
So that's a quicker way of doing it. Is that okay? So ideally, look, removing 1, we want to check the remaining is strictly increasing. So it's the same thing as let's find out the longest increasing subsequence of this. If the length of the longest increasing subsequence is n minus 1 or more, right?
Yeah, peel,
Then,
peel,
then
peel.
it's essentially the same as removing 1, right? It's the same thing. Yeah? These two problems is the equivalent, right, Ryan? Am I right?
Yeah.
Does it make sense? Yeah. Okay, so do you still remember this longest increasing subsequence? Yeah, we talked about that like 100 days ago. Yeah. You probably don't remember. Yeah, that's fine. I'll remind you. Okay.
Hey, my shoe is broken. Kind of. See?
So for the longest increasing subsequence, we have two approach. One is O(n) square, yeah. One is O(n) log n. Okay. So let's go to the longest increasing subsequence with the O(n) square approach, which is dynamic programming. Okay. So do you still remember what's dynamic programming?
Yeah, you need cat.
Memorization.
Memorization.
up.
Pass.
So let's say.
Down.
Okay. Come on. Array equals 1, 5, 2, 3. Okay. So let's say if we have a f function, fi. Fi means the longest increasing subsequence that ends at index I. Okay? So it equals what? Maximum of what? Fj plus 1. If the number ARR j is strictly smaller than ARR I, and also the index j is smaller than I. Okay? For j is belong from the 0 to I. Okay? So that's the dynamic equation. So what do you mean? Fi means the longest increasing subsequence that ends at index I. Okay, Eric? Look, F0, F1 is here. So the longest increasing subsequence ends at that second number. So if we can iterate the numbers up to array I, yeah? If array I is up to array I, and then if we found the array J, the index is up to I index, and right? It's actually these two are the same, yeah? So we don't need to write it twice. So for J in 0 to I, if array J, if we found a number which is smaller, if we find a number which is smaller, look, 5 is smaller than 5, 1 is smaller than 5. Okay, so the longest increasing subsequence that ends 5 is equals to the longest increasing subsequence of ending at 1 plus 1, right? Yeah? Because look, I found this is Fi, right? This is Fi ending here. And then if I find another one here, J, which is smaller than I, so it means that I can use the Fj previously longest increasing subsequence that ends at J and plus 1 number because array J is smaller than array I. Okay? Makes sense, yeah?
What's that?
Oh, we're done. That means belongs to in. You see, okay? Let's say x belongs to 0 to 10. Okay? Then x, the integer, right? Will be 0, 1, 2, 3, 4, 5, 10. Okay? Yeah? Okay, or you can say in. That's in. Actually in. Okay? In. So if we implement this, that will be O(n) square. Okay, let's quickly implement this. Do you get this idea, every guy? Do you get it? Yeah.
No.
You don't. Do you want me to repeat again?
Nah.
Do you understand?
Yeah.
Okay. Okay, are you sure? Okay. So dynamic programming. Okay, the simplest idea is that okay. Okay. Simple idea. How many pens are there? How many pens are there? Right? How many pens are there?
2.
Okay. And if I put one more, how many pens?
3.
3. That's dynamic programming. Okay. So look Fi. Okay. So Fj, right? Fj is 2, and then I have another one Fi coming. I put it together. So Fi equals Fj plus 1. Because we don't need to calculate this portion again, Fi again, right? Because we save it. That's the spirit of dynamic programming. Minimization. What's minimization?
Minimization.
What does it mean in English?
Minimization is minimization.
Memory stuff, yeah, memory. Memo, yeah, memo. Remember. Yeah?
Memorization.
Memorization. Okay, good. That's it.
Minimization.
Okay, let's write this. Can you not touch my keyboard, please?
Ryan was writing on it.
Define. Okay, let's say I don't know what's the name of the function. Let's just call it I don't know, day 402. Okay, day 402. Array. Right? And then n equals the length array, and then we have a f function. F equals at the beginning 1 times n. Okay. So what? Any idea why we need to put a 1 initially? F the value will be 1. The longest increasing subsequence at in each index is what? At the beginning is 1, right? Yeah. Each number is the longest increasing subsequence, right? And then we can say for I in range n, right? And then for j in range I, right? If array j is smaller than array I, right? Then we can say f function f I equals maximum of fi fj plus 1. Okay? Now look, the longest increasing subsequent length return will be what? Come on. Will be the maximum of f function, right? Why is that? Can you tell me? If this plus 1 is bigger or equal than n, then we can remove one number and get this. Okay? Anyway, can you explain to this bit, and then if you can, I give you 2 programming tasks.
Return. Okay. You have to the max. You know the subsequence. Plus 1, which is bigger or equal than n.
Why we need to check plus 1 equal or equal than n? What's the problem? What's the original problem?
The original problem is to find the strictly increasing subsequence. So you figure out if you at most 1 deleting 1
Yeah.
at most 1 from the list 2, and then it will be strictly increasing.
Yeah, so at most 1, yeah? This is what it does. Why this is max f is the longest increasing subsequent?
It's because it's the maximum.
Why what's f?
F is
What did I say? The longest increasing subsequence what? Of what?
of
What? 1, look, 1, 2, 3. Okay, so what's the f value for the, this is the original array. What's the f value?
1, 2, 3.
1, 2, 3. Okay,
1,
okay,
2,
this is,
3.
1, 2,
okay,
3.
wait. How about 1, 5, 3?
Minutes.
What's the longest increasing subsequence?
1,
No.
3.
What's the f value?
The
1,
word is F is
2. What should I put here?
3.
No, it's not 3. What's the f value?
The F value.
The longest increasing subsequent that ends at current index. 1, 2. What's there? What should I put here?
You should put
What's the longest increasing subsequent that ends at index 3?
3.
The length, the long 2. Why is 2?
Because
Because you count index.
1 and 3.
Yeah.
So you understand what's f. So what's max f?
Max F is maximum.
Yeah, I know. What's the longest increasing subsequence? If I look, because f value is only gives me the longest increasing subsequence, the ends at each index, right? And I want to find out the longest increasing subsequence, the ends for the array. So it can end at any index. That's why I put that max f to get the longest increasing subsequence of the whole array. Plus 1, right? Because that's what we said. We need to find out if we can if we can have a increasing subsequence, increasing array by removing 1. So that's 1 where that come from, right? We have an array, okay? What's the time complexity? Come on.
Square.
N square, yeah. You see? Yeah. It's not better, right? It's not better, but this is another idea, okay? But we talk about the longest increasing subsequence by greedy using the biset left, biset right. Do you still remember binary set left, binary set right? It's a two functions to find the index to insert the element. Okay, look, array. This is array 1, 2, 2, 3, 3, 3, 4. Okay, so biset left, A. If I want to put the number 3. Every line, look, this is a sorted array, and biset left, yeah. I want to find out which index I can put the number 3 in. So biset left, you will tell me it's here, right? You will return 0, 1, 2, 3. So if I insert at this place, right? All the elements before is smaller than me, right? Smaller than 3, yeah. That's biset left. And how about biset right? You know, if it has a equal numbers, you will be the first one. Right? Biset right, you'll be here. Okay, it's slightly different. Look, because if I put the number 3 at here, yeah, A3 here, that position, I want to put another 3 here, right? So that would be on the right of the a block of 3 because it's the same. Right? And if I want to put a 3 using biset left, it will be on the left.
It'll be biset right.
Yeah. Do you get it? Yeah. Why are we using biset left right? Because we have O log n complexity for both two. Yeah. Both operation. Okay. So we are using this, and then we can do this. We can keep tracking of the longest increasing subsequence. Okay, so let's go through this 1, 5, 2, 3 again. Okay, so look, alright, longest increasing subsequence at the beginning is empty. Okay, 1. Where do I put the 1 in the here? It'll be there, right?
Yeah.
So I put the 1 here. 5. Where is the 5 going to fit here? On the right of the 1, right?
Yeah.
So if it's more than that, I'm putting 2. Where is the 2 going to be in here? Between, right?
Yeah.
So it's here, right?
Yeah.
So I will remove it and put it as 5. Why can we do it? Look, because we keep tracking of longest increasing subsequence, and we find a smaller number is less than 5, right? I can replace it. Do you get it? Look, I don't care what happens, the longest increasing subsequence in the future, but I know is that the result will not get worse if I replace 5 with 2. Am I right?
Mm-hmm.
Yeah, because 2 is smaller than 5. Yeah? If you have a longest increasing subsequence, you know, something like that, I can replace it with a smaller number 2. It still stands, right? Am I right? Make sense? So that means, okay, I just replace it. Okay, and now 3, where's it going to put? On the right of here.
Yeah.
Okay. So we have the longest increasing subsequence, which is then 3, okay? And it's bigger or equal than n minus 1. So yeah, we can remove it, okay? Let's do this. Yeah? Do you get it? Yeah? Ryan? Do you get it? Okay, let's do this. Define 402, okay? Alright. And then you need to tell me what's the time complexity for the last question, okay? Longest increasing subsequence equals at the beginning empty. Look at it. For I in array, and the index is what? Index, let's say x equals bisect left. Bisect left, bisect right are from bisect package. Bisect, it means the binary, binary. Actually, I don't know what bisect stands for. Okay, bi is for binary. Set, probably, I have no idea. Okay, bisect left, list, and I. Okay, look. Then if this index is equals to the length, if this insertion point is at the end of the position, at the end on the right, at the end, right? At the end of the list, then we can just do what? We can just list dot append x, right? As list x equals I. Yeah? And then return length of list is bigger, plus 1 is bigger or equal than length ARR, right? Yeah? Got it? Okay, so the same thing. What's the time complexity? What's the time complexity? Come on. What's the time complexity?
The time complexity is
This is n. What's this? This
okay.
N log n. Well done. N log n. Okay. Yeah, we're considering these as O1. Okay. Append is O1. Okay. And then changing a value at index x is O1 as well, constant. And can you tell me what's this bit? This should be similar to the last one, right? Alright? What's this bit? Length this plus 1 equals length AR. You just answered that 5 minutes ago. What's this bit?
That bit is the length of the list.
Yeah? List, what's this?
Plus 1.
What's this?
The list.
What's it?
It's the list.
What's this?
It's a list.
What does it mean?
It means that it's technically a list that you contain the answer in.
But I'm not returning answer. What's list? Long is what?
Longest subsequence.
Increasing subsequence. And then I wanted the length of longest increasing subsequence plus 1 bigger than that. Can you explain this to me? This is the idea of using this.
It's the length
Right?
of longest subsequence.
Yeah,
plus
the
one.
list with the longest subsequence.
If it's bigger than the length of an array.
Yeah? Why?
Two.
Why this works? You haven't explained that well to me. I mean, what's the problem? What's the original problem?
The real problem is you have a list
And
of numbers
yeah?
and you can delete at most one character
And-
from the list, and then when you delete it, the list should be totally strictly increasing.
Yeah. Okay, so that's the same as finding the longest increasing subsequence of the array. The length. Okay, so the longest increasing subsequence of array, which is, so look here, the list will be what? Can you tell me what's the list here?
1, 2, 3.
Okay, and the length is what?
3.
Okay, 3. And then I need to plus 1, that become 4. And then 4 is bigger or equal than the length of the whole thing. That means that if I remove one element and I can get the rest remaining numbers strictly increasing, okay?
Yeah.
And this is the most efficient ON again.
Yeah.
Okay, that's it for today. Bye bye.
Bye bye.
Bye bye. 讀咁單詞咧。Bye bye. Bye bye.
Bye.